It is 10:40 a.m., guys, and we are going to start. Before I move on with the discussion, good morning, everyone. Welcome to our discussion number 4. And if you haven't already, send me your email in the chat so I can add you to a Slack channel specifically for this discussion. I am definitely going to post screenshots of the songs that we have so far in the playlist, and you can always just send suggestions there too. Other than that, you can also use the channel to find partners for the quiz that you guys have to do, the one with the interview. And you can just send memes, honestly. I don't care. And I'll probably be sending memes too. It's just to chat among us. I wanted to send the invite through an email, but I don't know how many online students actually attend this one and how many attend Kevin's discussion. So I'm just gonna add anyone who sends me an email here. Before I start with the discussion, do you guys have any questions so far about the quizzes, about the material? I don't know how much you covered when it comes to trees. As far as I'm aware, you still haven't started with binary trees. So I would like to know what was the last thing you did with Professor Ahmad. Okay, so you covered the types of trees as in like what's a full tree, what's a complete tree, what's a perfect tree, etc. Right? Okay. Okay, I added everyone who sent me their emails so far. Okay, so right. So he talked about what an n-array tree versus a binary tree would be. Right. Okay, I'll go into a little more detail and talk about some binary search trees. Let's see where here. And the questions that you're going to have for participation, they're mostly going to be about the types of trees. So you guys don't have to worry about that. Let's see, what are you guys seeing? You're seeing the right screen. Once again, as with all the discussions we've had so far, feel free to ask questions in the chat, answer the questions I have for you guys in the chat. I'll monitor that as best as I can. And we're gonna get started with trees and traversals. So you guys said that Professor Aman covered what a binary tree would be versus any other tree, and that's obviously going to be the number of children each node has. So a binary tree can only have, each node can only have 2 children, as opposed to having any n amount of children for an n-array tree. Unfortunately, we're not gonna do Jeopardy because I would need you guys to be in person there. That's how we designed it. I'm so sorry, but I I'll come up with an activity specific for us that we can all do together, so you guys don't lose on that part. So starting off with the binary trees, we have obviously the regular parent node, 2 children, except with a binary search tree, the left subtree contains node values that can only be smaller than the root node that you're looking at. and the right subtree has to have all the nodes or all the values that that are greater than the root node that you're looking at. Both subtrees also have to be binary search trees. So if you look at any node, any node in the lower levels, so for example 6 here, if you look at this as a separate tree, it will also be a binary search tree. So 4 will be here and 7 will be here because it's greater than 6. Moving on, we have types of trees, which you guys covered. So full tree, every node has either 0 or 2 children. A complete tree is all levels are completely filled except possibly the last level, so the bottom one. And the last level has all the nodes pushed to the left as possible. So the way to create a complete tree would be just to keep adding nodes to the leftmost position that's available. So like starting this way. And then a perfect tree, it has all internal nodes have 2 children and all leaf nodes are on the same level. Perfect trees are both complete and full, but if your tree is complete and full, that doesn't necessarily mean that it's perfect. So it's not an if and only if type of relationship. And you're gonna have to keep that in mind. And now I have a poll question for you guys. So I'm gonna open that. Let's see, poll question number 1, launch. Which of the following options apply to the tree? And it's a multiple choice question to apply all the properties that apply. Honestly, you guys are doing good. Considering that Professor Aman has not talked about binary search trees yet. Okay, I'm going to end the poll now. Do you guys want to see the results or are you good? Let's move the poll out of the way. Anyway, so the correct answers are full and binary search tree. So a lot of you actually answered the share results. There, I think you guys should be able to see the way you did on the poll now. But when it comes to the binary search tree, a majority of you answered it correctly. And I think only a few of you didn't click that one. But yeah, it's a binary search tree because all the nodes to the left of 25 are less than 25. All the nodes to the left of 11 are less than 11. All the nodes to the right of 25 are greater than 25. And all the nodes to the right of 11 are greater than 11. And that applies to this subtree too. And then it's also full because each internal node either has 0 children, such as 51 and 14, which are leaf nodes, and 2 and 5, or it has 2 children, so 25, 11, and 4 are filled out. Let's see, next. Yeah, I already talked about this one. Next question. Let's see, launch. Which of the following properties apply to this tree? So far, honestly, guys, overwhelmingly better than the last question. So good job. And I'm going to open the poll. There we go. So the correct answers are, if the slide was swapped, there we go. Complete and the binary search tree. Once again, if you look at any node, all the nodes to the left of it are smaller than the value it holds. All the values to the right are greater than the value it holds. It is also complete because all the nodes at the bottom, all the levels are filled up first of all, and I'm going to talk about it, Andrew, now. So all the levels are filled up except for the last level, and in the last level, all the nodes are filled up from the left to the right. So this side of the tree doesn't have any children. The reason it's not, yeah, the reason it is not full is because 51 only has one child, and the requirement for a full tree is to have either 0 or 2 children. And yeah, let's go further. We have question number 3. Which of the following apply to this tree? And okay. So this one tripped you guys up a little bit. It is not a binary search tree because these two nodes are swapped. So 5 is not less than 2, unfortunately. So it's not a binary search tree, but it is a full and complete tree. Additionally, it is not perfect because this level here is not filled up completely. For a perfect tree to, well, for a tree to be perfect, all the levels have to be completely full. And yeah, so this is the explanation. Full question number 4. We have a lot of them, honestly, today, but it's good practice. Again, which of the properties apply to the following tree? And don't forget the properties of binary search trees before we move on. should have figured out a Menti to do this with you guys, but it was a little hard because it's multiple choice. But I'm pretty sure that I'll try to do it from next week and actually start giving you guys digital rubber duckies because you guys miss out on that in online sections. Okay. Question number 4. You guys did really well on this one. So the correct answer is A, B, and C. Yeah. So the tree is full, complete, and perfect. And the way I would answer this question is the tree is perfect itself. All the levels are filled up completely. Leaf nodes are all on the same level. So it's perfect. And because the tree is perfect, it means that it's full and complete. It is not a binary search tree because 25 here is greater than 14 and 5 here is less than 14. So those two would have to be swapped before you could have a, well, you would also have to swap 5 and 11. Anyway, it's not a binary search tree. When it comes to binary trees, perfect binary trees that are obviously full, right? But if you have a height of h of your full binary tree, a perfect binary tree will have exactly 2 to the h minus 1 nodes, and you can easily get that. So like each level adds a height of, like, this case is 3 is equal. And at this level we have 4 nodes, at this level we have 2, and at this level we have 1. So each time you go down 1 level, you double it, hence the 2 to the power of h. And then you remove 1 because the root level has only 1 node. Okay, moving on. We have some reminders. So full tree is not necessarily complete. A complete tree is not necessarily full. A perfect tree is always complete and full, but a complete and full tree is not always perfect. Keep that in mind, and I would honestly have this slide somewhere on like a sticky note while you're studying for exams, etc., or quizzes. Tree traversals, I don't know if you guys covered this in class already, but there are basically there are several ways you can think about traversing trees. You could go with depth first, which I think I talked about in previous discussions, but I'll go over it again. Or you could go breadth first, but we're gonna talk about depth first traversals first. There are 3 types of depth first traversals. They're called pre-ordered, in order, and post-order. And these are little short, like, anagrams of nodes that you will visit at each stage for each traversal. N means visit current node. L means visit nodes that are to the left or in the left subtree. And R means visit nodes in the right subtree. So let's see. If breadth first search, it's about fanning out the search. It's not going like to the furthest away point. It's like having a really wide area search where you basically go level by level through the nodes and check if it's the node that you're looking for. You could do it in different ways. You could like always enter from the left side or always enter from the right side, which is what this image here displays, or like the spiral approach, where you can imagine that you're like rotating around the tree, so you're always checking the nodes from the same side. Or you could do the zigzag approach where you enter each level from a different side. So you enter 5 from the left and then go with 10, go to 15, and then 35, etc. I'm gonna go back to the depth first searches just to go in a little more depth on the explanation. This image here has all types of the depth first traversals and searches, but if I really wish I knew how to zoom in. Anyway, oh, I think I do. Yeah, there we go. Anyway, it doesn't let me. It doesn't matter. So when it comes to the pre-order traversal, which is gonna be our blue track here, and I'm gonna also hopefully change. No, it's okay. Follow the blue dots here. You go to the current node, enter the root node, and pre-order traversal first visits the node that you're at, the current node, then goes to the left subtree, and then circles back to the right subtree. So the way the path looks is you visit this node here, and then you move to the left subtree, you visit this node here, then you move to the left subtree again, and you visit this node tree here, and then you move to its left subtree again, and you go and visit this node. Once you're done with this one doesn't have any left children, unfortunately, so we can't keep moving forward. Then you move on to the right subtree of node D, visit this one, and then you go all the way back. You go to E, and you go all the way back and go to C. C has a left child, so you go to F. F doesn't have any children, so you go back, etc. Let me clear the ink. There we go. When it comes to, that was pre-order, and the way that you could think about memorizing it is pre-order, you visit this node first, which is not necessarily the most ordered way to access nodes. If you think about a binary search tree from like previous slides, for example, let's see, where's my, yeah, this is a binary search tree. If you visit in order, you're gonna visit 14, and let's say that you're just printing out nodes, you're gonna print 14 and then go to 5, and then you're gonna print 5, and you're gonna go to 2, print 2, and then go to 11. And this has not necessarily any order. And you visit this node first, it's the root node, and thus it's called pre-order, right? Because the something about visiting the root node is called pre. And then we have the in order traversal, which is the best one. And in this one, you visit the left subtree first. Then once you're done visiting the left subtree, you move back to the original node, you visit that node, and then you go to the right subtree and visit the entirety of it. So the way you would do it on this tree that we have here is you would enter the tree here, but you won't do anything with node A. You would move to node B. And because B also has children, you won't do anything with this node either. You're just going to move on to D. And then D also has, especially left child. So you're going to move on further to H. H doesn't have any children. It doesn't have a left child, especially. So that means we move on to that node, and then we visit H, and you print out H, which is what is happening here if you look at it. Once you're done with H, H doesn't have any children, so you move back to D, and then you visit D, so you print out D. Then you move to I, because it's the right child. You visit I, and then you move back up to B. You visit B, and then move on to the right subtree, which is going to be E, because E doesn't have any children, etc., etc. You're going to keep moving on. And once again, about the naming of the traversal, if you think about visiting a binary search tree, we're going to start with 25, but we're not going to visit it yet. And we're going to go to 11 because 25 has that left subtree. We're not going to visit 11 yet. We're just going to move on past it because it has that left child. We're going to go to 4, not visit it because it has a left child. And then we're going to visit 2 because 2 doesn't have any children. We're going to print out 2. And then we're going to go back, visit 4 because that's in order traversal, and then go on to the right child, which is going to be 5. Then move back to 11, go to 14 because that's the right child, following the left L and R approach. We're going to visit 14, move back to 25, back in the N node. 25, that was a really ugly 2, I'm sorry, guys. And then go to 51. And when you look at the way that these nodes are visited with a binary search tree, they're visited in the growing order, and hence why the traversal is called in order. And then the last one we have is the post order. And because pre-order was visiting the original node, the current node first, the post order is then doing the opposite and visiting that one last. So you move on to the left subtree and then move on to the left subtree again, and then move on to the left subtree again because they have children. H doesn't have any children. So you visit it, you move on to the right child of D because that's unfortunately our current node, and visit I, and then go back and visit D. And then you do the same thing where instead of going back to B, you go to E, visit E, and then go back to visit B. And then instead of visiting A, you move on to C, but C also has children, so you move on down to F, you visit F. Instead of going back to C, you go to G. G also has children, so you go to J. And then you just loop back. And usually the best way to recognize post order is the last, if you look at the like completely right branch, like this one, A, C, and G in our case, those letters will always be read from the bottom up, and they'll always be in that line GCA at the very end of the traversal. So that's one quick way to recognize post order. Do you guys have any questions so far about this? Thumbs up in the chat if you're good to move on, and questions if you have any. Yes, Alexander, that is how you can implement it with a loop, but it's honestly the best way to do it recursively. And yeah, that is just the way you enter nodes. I'm pretty sure that at some point when you start writing algorithms, yes, Seth, I'll explain pre-order again. Just give me a second. So once you start writing algorithms, for example, for an in order, they'll look something stupid like if your traversal function is called in order, the way that it's gonna look is in order left current and then in order right. And it's super stupid, but this is exactly how you make an algorithm for traversals. Well, I'll go back and explain pre-order again. So pre-order always visits the current node first. So if we enter the tree at the node A, you visit it first. So for example, if you want to print it out, you'll already be printing out A. And then it's going to move to the left subtree and enter B and visit B because that's our current node at this point. So it's going to print B. And then it's going to move even further down to the left child because B has a left child. Visit D while it's at it, print out D, and then move on to H and print H out. And once it's done with the left, going all the way down left, and that's also a way to recognize in order if you look at it in the same way as you look at the post order. You start from the top and read them all down this way, and you'll get your in order traversal um, or in order visit, I guess. Fine. Okay. Uh, let's move on then. We have a poll question number 5. And okay, it's launched. What is the pre-order traversal of this tree? Yeah, guys, you did so good. Good job. This is an overwhelmingly good result of a poll. I'm so proud of you. Okay, I am going to end the poll now just because we have to finish everything. The correct answer was B, like the 90% of you said it was. Obviously, first marker is the 531. You visit 5, you visit 3, you visit 1, and then you go on with the rest of the nodes. The way the traversal is going to look is if you follow the cursor, it's going to be 531, and then it's going to go to 2, and then go to 4, and then go 6, 8, 7, 9, and end there. Okay. Next poll question 6. Okay. There we go. What is the in order traversal of this tree? This one seems a little more hiccupy. Okay, I am going to end the poll now. So the correct answer is A. And as I mentioned before, if you have a binary search tree, which is what we have right here, so all the nodes are relatively sorted, the in order traversal would return a literally in growing order list. So just to follow down the, yep, Alex, it happens. So follow the cursor for the visits. We're gonna go to 5, but not visited. 3, not visited. 1, 1 doesn't have any left children here, so it's gonna visit 1 and then go to 2. Then it's gonna go back to 3, visit 4 after it, and then go back to 5. Visit 6 because 6 doesn't have any left children. It's gonna visit 7 because 8 does have a left child. Visit 8 and then 9. And it's going to follow obviously the left or left current and right node. So L and R. Next poll, we have a post order traversal. Yep. Wow. You guys are really good at this. Okay, I am going to end the poll because you guys also have to do the quiz. You a vast majority of you guys got this one right. It's C. And once again, remember the marker for post order. Yeah, it wouldn't be Alex, you could technically search the tree in any of these ways. This is just a way to like go over all the the nodes. There is a better way to search a binary tree. And that is I'm pretty sure it's called something like that, the binary search algorithm that you should have covered in programming 1 or 2. Anyway, we talked about all of this and we have more polls, but I'm not going to cover these right now. You guys have to do your quiz. So I am just going to stop sharing, go share the access code with you guys. If you look at the slides that we have, they don't give you any specific implementation. They do say it's the fastest or the best to do it with a queue. I would assume just because it's gonna traverse the tree in like level order and then use a queue to pop the nodes as they're added to check them in a searching while they're searching. So if you have like suppose we have a queue here, call it queue, and you traverse the nodes at each level. So you hit one on the first level, you add it here. And you add here 1, you go then to 2, you add 2, next node at that level is 3, and then you move on to next level, that's going to be 4, and then 5, 6, and 7, etc. You've traversed the tree in level order, so you've done it you've covered each level first before moving on to the next level. And then you use the queue property that the first one is going to be popped to search them. So you essentially check if peak queue is whatever you're looking for. Let's say that you're looking for some I, then you do whatever you want with that node, else pop. And then you keep moving on because it's going to pop this one. And then the next one you're going to look at is going to be 2. And then you're going to pop it. And then you're going to look at 3, etc. And that way you will be searching it the way you traversed it in like the level order. Does that make sense? Okay. And I have a few poll questions that talk about depth and breadth first searches, I guess. I don't understand why they put the transitions here. It's not like I'm not gonna draw myself anyway. But yeah, so this one's about the doing a breadth first search algorithm. So you're gonna visit each node however you want to do it, and that's where the multiple choice comes in play. You could be visiting them like this, or you could visit them like this. And you have to account for both of those when you check which answer would be correct. So right here, if we do the, I think this is called the like spiral approach. You would visit 5 and then go to 3 and 6 and then 1, 4, 8 and then 2, 7, 9. So this would be the correct answer. And if you do the zigzag approach, you could do 5, 3, 6, 8, 4, 1, 5, 2, 7, 9, which is 5. I don't think we have that one, but that's a valid one too. Or you could do the other way where you do 5, 6, 3, 1, 4, 8, 9, 7, 2. And all of these ways to get levels are valid. And I think that's the one, this is the one that we're looking at. So it's the one that goes to the right. They're all valid and you're gonna have to account for that when you do exams. Don't worry about it. I mean, you're gonna have it on this quiz and use that quiz as a practice. But I will keep reminding you of this throughout the semester. So today we did the polls about the questions for this discussion. Next discussion, I might just add questions about algorithm analysis, or the discussion about after that, I might just add a question about traversals, just to keep you guys on your toes and remind you of like all of the things we covered so far. And then this is something that you guys will have to cover with Professor Aman. But yeah, do you have any other questions for me?